In this video, I'm going to talk about a ball on a spring device. And in a nutshell, what we're going to do is we're going to put a ball on a spring, compress at a certain displacement, and launch it up into the air. And we're going to analyze this in terms of energy. So the first thing is this. You have an uncompressed spring. I'm going to denote this distance here of the uncompressed spring as 0. And then we're going to put a ball on top of this spring right here, and it's going to compress a certain distance, and that distance is given to be 10 centimeters. So I'll say this is 10 centimeters right here, and then we're going to further compress it with our hands another 30 centimeters, so a total of 40 centimeters displacement with the ball on top. And then we're going to, from here, let it go, and the ball is going to launch up in the air, and I'll show that final position over here, and the ball way up there, let's say. And that's the maximum height, and we want to find out what the maximum height the ball reaches. So we have an uncompressed spring, we put the ball on top, it compresses 10 centimeters, we push it down an additional 30 for a total of 40 centimeters, and then at that point we let it go and the ball shoots in the air. So we want to find a couple things here. The spring constant K, the potential energy stored in the spring, and that's at the 40 centimeter mark. That's the problem. We want to find the change of potential energy from the release point right here to the maximum height, that change of potential, and then the maximum height reached by the ball. So for the first part, the spring constant, if we know that a certain mass of the ball, therefore a certain force is applied to it, and it displaces 10 centimeters, we can use Hooke's law to find that spring constant. In the lab, we've actually used multiple data points, but here you can assume that the other data point is 0, 0. For 0 force, I have 0 displacement, and so then you can find the spring constant. For part B, the energy stored in the spring at the 40 centimeter part is the equation for the energy stored in the spring, 1/2 kx squared, and you know K from the previous part, and you know the compression is 40 centimeters. Then we start to go into the energy part, the change of potential energy and the H max. So I'm going to analyze this motion from the release point, I'll call that point A, to the maximum height reached by the ball, point B. I'll analyze this interval of time. So at point A, and the first step of the conservation of energy model is to draw the reference line. Since this is the lowest point it goes to, I'll denote point A as the reference line right there. So I draw it right on there. Check, we're done. Then I'm going to go to each bucket and see what energy exists. So if I hold this thing in place, there's no kinetic. At the launch point, I have no potential because I'm at the reference line, but I do have some potential due to spring because the spring is compressed. So I have that energy there. At the very, very top, when the ball reaches its maximum height, I have no kinetic. That's when it stops. I do have potential because it's above the reference line, and the spring is neither stretched nor compressed, so I have no spring potential. And there's no work done by friction because no forces of friction or air resistance are described. So the solution part. So here are my buckets, and I actually can address this right here, my change of potential. But change of potential is final minus initial. So if I can find this value here, final minus initial 0, the difference is my change. So whatever this number is. So for part C, the change in G is UG at B minus UG at A, and this is 0. So this basically becomes UG at B, which is MG Y at B. And if you look at that, you go, that's great, except I don't know the height at B. I don't know how high it rises. So we actually have to go to part D to find that height. So let's use conservation of energy. Using conservation of energy, I have my spring potential energy, 1/2 K x squared, and that x is at the 40 centimeter mark, equals mghb. So if I can solve for h of b, because I know k from the first part, I know this x is actually 40 centimeters, and m and g I know, I can solve for h of b. and get a height. And then I can say, well, if I know that height, I can find the change of potential. One other thing I want to mention about this problem is that the distances are given in centimeters, so we want to make sure we convert to meters so that we're all in meters and we get the correct amount for numerical value for joules. So there's the ball on the spring problem.